So here's a problem where we need to draw the additional resonance forms for the given compound, and then when we're done we can evaluate them and rank them on who looks the best and who looks the worst, and therefore how much do they contribute to the overall hybrid. So right away I see that I have an allylic lone pair, and so when I have an allylic lone pair, there's two arrows I can draw. Lone pair becomes a pi bond, and then pi bond becomes a lone pair. And so the result of that now is I'll have a pi bond here, a double bond between the carbon and the oxygen. Now there'll just be two lone pairs on that oxygen, and now there'll be an extra lone pair on this carbon. The other pi bonds haven't been involved, so we'll keep those there. And this top carbon now has 1, 2, 3, 4, 5 electrons, and that would be an anion, so that would be a negative charge on that carbon. And now we continue with our allylic lone pair resonance. Lone pair becomes a pi bond becomes a lone pair, and the result of those two arrows has a pi bond here, and now the extra lone pair is on this carbon, and we can finish up the rest of the structure that hasn't changed. And so now the carbon on the bottom left here has 1, 2, 3, 4, 5, and so that's where a negative charge is on this carbon. And we're still an allylic lone pair. So eventually we're going to end up using all three pi bonds that are in the ring. So lone pair becomes a pi bond becomes a lone pair. But it's important to do it just one at a time. Focus in on kind of this 3-atom system. So notice we have every allylic system is just 3 carbon atoms. We have the one atom with the lone pair, and the other two have the pi bond, and so that's what we can focus on. So when we finish that drawing, and we can keep our other pi bonds the same, but now we have a new pi bond here, and our lone pair is here, and which means our negative charge is done on this carbon. And then finally there's actually one last allylic lone pair we can do. Lone pair becomes a pi bond becomes a lone pair, and which actually brings us back to the negative charge on oxygen. And you might think, well, that's actually a resonance form we already have, but when you compare this first structure and this last structure, you see that the pi bonds within the ring have changed location. So this is actually a new resonance form as well. So when we look overall and we try and decide which are the best resonance forms, we would say that the first and the last are the best because we have a C- versus an O-. So these two are the best. They're equivalent because we have a negative charge on the more electronegative oxygen. And then the other three are all equivalent, and those are second best. So our explanation would be the best is the negative charge is on the more electronegative oxygen. Now this problem would be a lot easier to do if we just worked with line drawings. It takes a little practice though. Oops, let's redo that, sorry. That takes a little practice. And now with a line drawing we just leave off our hydrogens that are on carbons, and then we just represent carbons as the 6-membered ring as this hexagon. And so this just makes our drawing so much faster and easier. We could still see our allylic lone pair. Let me do that in the red again. Our allylic lone pair becomes a pi bond becomes a lone pair, and then it's so much faster to draw just this 6-membered ring. But then it's a little trickier when we go to calculate the formal charge. We have to remember that this top carbon had a hydrogen on it, so that's where the negative charge is, and the negative charge is going to continue following that lone pair around the ring. So we could do again, lone pair becomes a pi bond becomes a lone pair, and so on. Okay, so just wanted to show you what those line drawings look like. As we get more practice with those, that's really going to save us a lot of time.